So now based on all these concepts what we learned till now, that is the electric field intensity, electric flux density, and mostly very important one, that's Gauss law, potential, we will solve few important problems that we will learn how to apply our Gauss law in real time environment. So problem 1, given that the electric flux density D equals to Z rho cos square phi Az coulomb per meter square, then the charge density at point 1 pi by 4 3 is, that this is a problem. So as per our formula, as per our problem, so D is given to us, that is the electric flux density is given. At some point P we need to calculate the charge density. So he is not mentioned anything, so what is the type of charge density we are supposed to calculate, but we need to observe that one, so based on the basic concepts what we learned. So this D is directly related to the volume charge density. So here what I assume is this charge density is volume charge density what we are supposed to calculate. Now before calculation of this volume charge density, we need to observe few more points. In which coordinate system the parameters are given to us, and where we have to calculate the charge density or electric field intensity, etc. So first observe in which coordinate system the given parameters are. D is given as Z rho cos square phi Az. So for any information what we have, the unit vectors gives us the important information related to the coordinate system. So here the unit vector is Az. Since the unit vector is Az, we need to take this one maybe in Cartesian coordinate system or cylindrical coordinate system. So Cartesian coordinate system contains Az. Cylindrical coordinate system also contains Az. So we are supposed to take in these two coordinate systems only, wherever it is applicable, just we will examine a little bit later, right? So Cartesian coordinate system also contains Az, because cylindrical coordinate system also contains Az. Now so apart from these two, so among these two which one is most suitable, or exactly in which it is given, just observe the point. The point has 1 pi by 4 3. 1 is distance, pi by 4 is angle, 3 is distance. So in our rectangular or Cartesian coordinate system, 3 coordinates are only distances. In cylindrical coordinate system, 2 distances, 1 angle will be there. In spherical coordinate system, 1 distance, 2 angles will be there. So the spherical is already eliminated. So among these two, we need to eliminate this Cartesian also, because it contains 1 angle and 2 distances. So clearly the point was given in cylindrical coordinate system. Therefore we are supposed to take this D also in cylindrical coordinate system. That already we have this phi rho Z. So with that observation also we can say that it is given in cylindrical coordinate system. Right. Now what is the equation which is related, sir? D with this rho V. Already we know del dot D is equals to rho V, that is most useful equation, so called as our Maxwell's first equation. This del dot D is equals to rho V, here we have to apply. The divergence of this D will be considered for calculation of this rho V. Now this del operator will be considered in cylindrical coordinate system only. So consider this del operator in cylindrical coordinate system. So directly what I do is I will write down the divergence operation here. That so 1 by rho dou by dou rho of rho d rho. Directly I am writing the divergence of D here, plus 1 by rho dou by dou phi d phi plus dou by dou z dz, which is nothing but the divergence of D is equals to rho V. That what we have here. And observe, d rho is the rho component of D, d phi is the phi component of D, dz is the z component of D. With the observation clearly you can say that d rho is 0, there is no rho component here, there is no a rho term. In the same way d phi component is also not there, so they are not present in this one. So clearly this term becomes 0, this term also becomes 0, and only what we have is dou by dou z of dz. So dou by dou z of what is dz component? This z rho cos square phi. So z rho cos square phi is nothing but our rho V. So clearly the differentiation of this particular quantity is rho cos square phi, which is simply equals to our rho V. Now where we require this rho V? At some point P 1 pi by 4 3. So instead of rho substitute 1, instead of phi substitute pi by 4, instead of z substitute 3. So clearly this one will be calculated at 1 pi by 4 3. So if you substitute rho is equals to 1, simply it is 1. Cos square phi, cos square pi by 4, cos square pi by 4 is just 1 by 2 and there is no z term here. So simply it is 0.5. So clearly the charge density what we calculated for this particular problem is rho v is equals to 0.5. Now don't forget to write down the units. Volume charge density, that's why it is coulomb per meter cube. So this is our answer. Problem 2. So what is electric flux density? It's asked in microcoulomb per meter square at a point 64 minus 5 caused by a uniform surface charge density of 60 microcoulomb per meter square at a plane x is equals to 8. So here as per our given data, so we are supposed to calculate the electric flux density D in microcoulomb per meter square at point P 64 minus 5. So this is the point where we are supposed to observe our electric flux density, and that is because of a surface charge. A uniform surface charge is given to us with surface charge density rho s 60 microcoulomb per meter square, and that particular surface charge is located at x is equals to 8. So this is the given data. So here what we have to do is we have to imagine how the charge is placed and where we have to calculate. This is completely related to the three-dimensional problems. Yes, everything is three-dimensional. So we need to relate them with the three-dimensional coordinate systems. Since it is given in x is equals to 8 plane, take the rectangular coordinate system. So in the rectangular coordinate system, so take the basic one x, y, z, where the plane was placed at x is equals to 8. So let us take at x is equals to somewhere 8 the plane was placed. Just imagine it. Whenever we are placing a particular plane at x is equals to somewhere, some quantity, then that will be parallel to the yz plane. So let us take this is the yz plane what we have, and this is another plane what we are placing at x is equals to 8. That may be x is equals to 8 or 5 or 16, whatever it may be. So if you are placing a plane at x is equals to 8, obviously that will be parallel to the yz plane that what we are considering. So here a plane with uniform charge density rho s was placed maybe like this. So this is the sheet what we considered. That sheet was placed in parallel with the yz plane exactly at x is equals to 8. Now because of this sheet, what will be the flux density we require? Already we have a general formula. The flux density D is equals to, a direct formula is there, just rho s by 2, and the direction is normal to the sheet. Already rho s is given to us 60 microcoulomb. So an we require. Now what is that an? A normal vector which is drawn from sheet to the point. So what we have to do is we have to observe a vector as a normal which is drawn from sheet to the point. Now where the point is? The point is as given as 6, 4, minus 5. So here the x coordinate is 6. So somewhere the point is behind the sheet from our side. So if I am viewing the yz plane like this, x is equals to 8 plane is here, yz plane is here, x is equals to 8 plane is here, and the point 6, 4, minus 5 is behind the sheet what I am considering. So what I have to draw is just I need to imagine it's initially. So that this is the sheet what I have, it's on that sheet the charge is there and the point is behind this sheet. So if I draw a normal from the sheet to the point, how it will be? Always that will be in the direction of negative x-axis. Just you observe that. So somewhere the point is there, and if I draw a normal from this sheet to that particular point, this is always in the direction of negative x-axis. So a normal which is drawn from sheet to the point is now minus ax. Just substitute here. Then what is rho s? 60 microcoulomb divided by 2, and instead of this normal vector I will write minus ax, that is 30 microcoulomb minus 30 microcoulomb ax. The answer was asked in microcoulomb per meter square, right? So simply it is minus 30 ax coulomb per meter square. So minus 30 ax coulomb per meter square is our answer. Problem 3. Two coaxial cylindrical sheets of charge are present in free space with rho s is equals to 5 coulomb per meter square at r is equals to 2 meter and rho s is equals to minus 4 coulomb per meter square at r is equals to 4 meter. The displacement flux density d at r is equals to 3 meter is. Here, as per the data given in our problem, two cylindrical sheets are given to us. They are not plain sheets. So, two cylindrical sheets are given to us and those two are coaxial sheets. Those two coaxial sheets are placed at r is equals to 2 meter. They have r is equals to 2 meter. So, radius is 2 meter. This radius is 4 meter and the charge density for this particular sheet is 5 coulomb per meter square and for this sheet is minus 4 coulomb per meter square. So, we require some electric flux density at r is equals to 3 meter. As I said, so here if you take the pictorial representation of this one, this is very easy to solve. So, we need to imagine that, but little bit. So, the imagination may be little bit difficult. So, what I do is I will take the cross sectional view of this one. From the top side, if I observe those cylinders, how they looks. Now, draw this cylinder. This cylinder has radius of 2 meter. That one cylinder has a radius of 2 meter and the charge density on that one is 5 coulomb per meter square. That is a charge density for this particular cylindrical sheet. So, the sheet length was not given. Do not bother about the sheet length. Okay, for some time just you take the cross sectional view from the top side. Now, it is a 5 coulomb per meter square. Next, one more cylindrical sheet was placed at r is equals to 4 meter. So, the diameter of this particular cylindrical sheet is now 4 meter. So, let us take a 4 meter diameter cylindrical sheet. So, let us take this is a 4 meter diameter cylindrical sheet and on that one the charge is uniformly distributed with this quantity minus 4 coulomb per meter square. So, let us take this is the sheet 1, this is sheet 2. The charge density on sheet 1 is 5 coulomb per meter square, charge density on sheet 2 is minus 4 coulomb per meter square. Now, we require the electric flux density at r is equals to 3 meter. So, somewhere at r is equals to 3 meter, so this is the r is equals to 3 meter zone. That at this r is equals to 3 meter, we require the electric flux density. How to obtain the electric flux density? It's a very easy. As I said, our Gauss law is very much useful here. If we can apply the Gauss law here, it's in an easiest way we can obtain the equation. We can obtain the relation between all the quantities what we have. Just what is our Gauss law? The total flux leaving through the Gaussian surface is equals to the total charge enclosed. So, here what we are supposed to do is we need to form a symmetrical Gaussian surface. So, a symmetrical Gaussian surface at the point what we require is a cylinder. That what we have drawn here, that this dotted cylinder is nothing but the Gaussian surface what we are supposed to consider. So, already the Gaussian surface was formed, right? Now, just to calculate the total flux leaving through the Gaussian surface. So, what will be the total flux leaving through the Gaussian surface? The total flux leaving through the Gaussian surface always will be in the radial direction, that we can calculate that one using its flux density. So, the total flux leaving through the Gaussian surface psi is equals to integral d ds. That what we have, right? So, this d is uniformly distributed, that what we are assuming on the Gaussian surface. So, the location what we are considering is now become Gaussian surface, right? So, here what we have to do is we have to calculate the total flux leaving through that Gaussian surface. Therefore, this d is uniformly distributed on that Gaussian surface. So, surface integral of d ds, which is equals to, since it is uniformly distributed, so don't bother about directions for some time, as we know that is radially outwards, just leave it. So, d integral ds. So, this integral ds will give us the total surface area of the Gaussian surface. So, what is the surface area of any cylinder? Surface area of any cylinder for the curved surface is 2 pi rho L. So, which is equals to d 2 pi rho is nothing but the radius. What is the radius up to this part? It is 3 meter radius. 2 pi into 3, we don't know what is the length of the cylinder. So, don't bother about that, just you write down that one as L. So, clearly observe what I am doing here. I am trying to calculate the total flux leaving through the surface. That surface is a Gaussian surface, that what I am assuming. that Gaussian surface actually has three surfaces, a curved surface, top and bottom. Since D is radially outwards, the top and bottom were neglected. Already we discussed that one, and I am taking only the surface of our curved one. So the curved surface area is equals to 2 pi into 3 into L. This is the total flux leaving. Now what is the total charge enclosed? The total charge enclosed can be calculated using this charge density. Here what we have is a surface charge. So using this surface charge we can calculate the total charge, right? So the total charge enclosed is equals to integral rho s ds. So already rho s is given to us, right? Now observe, so which rho s we are supposed to take? We have this rho s as well as this rho s. So two surface charge densities are there. This has surface charge density of 5 coulomb per meter square. This has surface charge density of minus 4 coulomb per meter square. But clearly remember that, so we are always supposed to take the charge which is enclosed within the Gaussian surface. So whatever may be the charge which is outside the Gaussian surface, leave it. Don't bother about that. So what is the charge which is enclosed within the Gaussian surface? Only 5 coulomb per meter square. Take that one only. That rho s is only 5 coulomb per meter square. So clearly write down this one as surface integral of rho s, that is 5 coulomb per meter square, that's right, ds, this is 5, that what I am substituting, since it is a constant, bring it out. Then what we can write is 5 integral ds. Now what is this ds? This is the differential surface which is integrated to obtain the total surface of charge, right? So clearly we need to suppose the area of this particular charge, that is nothing but the cylindrical surface. So what is the surface area of this cylindrical surface up to this particular point? The radius is only 2. Since the radius is 2, this differential surface can be written as 2 pi, radius is 2, we don't know the length of that one, we assume that the length of the inner cylinder and the Gaussian surface both are same. That's why I will consider this one as L. So clearly observe, initially I am calculating the total flux leaving through the Gaussian surface and the total charge enclosed within the Gaussian surface. So the charge was enclosed up to this particular part only. That's why it is 5 into 2 pi into 2 into L. So if you simplify this one or if you equate this one, then what we get is here d 2 pi is 6 pi L, which is equals to, here it is 20 pi L. So this pi will be cancelled, L will be cancelled. Therefore d is equals to simply 20 by 6. So that's a very simple answer, 20 by 6. But what is the direction? So don't forget to write down the direction, because this d is a vector quantity. Always we are supposed to write down the direction of that one. What is the direction of our d? Always radially outwards. Since d is radially outwards, just you add the direction a rho. So therefore the total flux density at r is equals to 3 meter we have calculated as 20 by 6 in the direction of a rho. This is the answer.